let's get going. Don't have much time. Let me just review what we've got for homework. So you should have turned in homework 4 and homework 7, uploaded to D2L. 4 was the STL file for the Lego, rapid prototype Lego. 7 was the creating 2 parts, 2 drawings, and an assembly. That should have been uploaded. Assigned tonight was supposed to be the SolidCam video tutorial. I'm gonna go ahead and move that till tomorrow. So don't worry about that. We'll move that guy, and I'll re-upload this calendar up to D2L right after class. All right, so you're gonna have a couple. So you need to watch the CNC knee mill video, and you need to watch the do the SolidWorks tutorial patterning features, and then you need to. Homework 12 is going to be assigned due tomorrow. Homework 12 is taking your piece from homework 10 that you sawed out, that's this piece, and affixing it to a milling machine such that when we write a tool path, we'll be able to cut this out. Now, you guys have done fixturing lectures in there. You did fixturing lectures, so you saw how to clamp pieces down to a table. Did you see toe clamps? The little block clamps? Okay, so you should be able to do this. Homework 12 is to clamp the piece that you cut out onto the milling machine. Now, how many groups do we have? 7? Is it 7? Right? Is it 6? Show me a group. And actually, let's just one at a time. Show me a group. Your group. That's you 3. I'm going to assign you number 2 because when we go to engrave on this, I want you to be number 2, unit 2. Okay? Show me another group. It's you guys. You're 3. Show me another one. You're 4. Show me another one. This one. You're 5. Show me another one. You're 6. Show me another one. That's it? 6 groups. Okay. There's machines back there. There's 3 machines. There's the 2 bed mill types. One is called Vale, and one is called Copper. And then the one in the corner is a knee mill type. It's called Wolf Creek. Max likes these names. I want you guys to distribute yourselves amongst these machines well. So I want one group on Wolf Creek, and then that leaves 5 groups. Let's go ahead and try and put 2 or 3 onto Vale. It's got a much bigger bed than these 2. And let's try and put 1 or 2 on Copper. I want to try and maintain, we've got a grad student working on a project in there, and he's got a vise over here. So I want to maintain that vise on that machine, so that the groups that come over here need to be on the left-hand side of the machine, of the bed. Okay? So we're probably going to want to do 3 or 4 plates over on Vale, and 1 or 2 on Copper. Let's go 2 on Copper so we can distribute the load on the machines. 3 on Vale, 2 on Copper, 1 on Wolf Creek. One more hint for you. Orient your plate either, remember you have a bandsawed plate, right? Either orient it like that or orient it like that, horizontally or vertically. You don't want to orient it like this, because the tables move this direction and this direction. You want to orient it pretty well on an axis. And the way you can do that is there's a whole bunch of holes in the table. Try and line up an edge fairly parallel or perpendicular to a line of holes before you clamp it down. Got it? we should probably have them. Let's have you toe clamp it in the corners. So toe clamp it in the corners as shown in your fixturing lecture. That's all the hints I'm going to give you. So your homework 12 is to literally clamp that piece down onto the table. What I want you to do is take a Sharpie marker and write all 3 of your names on that piece once you're done, so I can go to the machine, look at the piece, and grade you on your fixture. Questions?
Will Sharpie come off in the end?
But yeah, you can take it off with alcohol.
So by 9 tomorrow, we want a fixture to be...
Correct.
So can I add something to that I didn't cover in the fixturing lecture?
Go.
So if you remember on the tables, there's all the tapped hole patterns. Sometimes those tapped holes get messed up, or when we surface the machine, they'll get a little burr over the tap. So it's difficult to get the screw into the tapped holes. So what you should do is first blow it out with air, and then see if your screw or your bolt will go into the tapped hole. If it does not, then we need to help you, at least show you the first one, to use a half 13 tap from the cabinet and clean out the hole that you want to use.
We'll help you with that. If a screw doesn't go into a threaded hole in the table, come find one of us and we'll help you fix that hole. Anything else?
No. You told them to make sure that the underside of their part was clean and the top of the table was clean.
No, I didn't. So that's a hint. He just gave you a hint. And you're through fastening lecture 2?
Right.
Okay. I'm behind, so. Okay, so assigned tonight is homework 12, locking that part down on the table, the CNC knee mill video, and the SolidWorks tutorial patterning features. Due tomorrow is homework 9, that's uploaded to D2L, which was a part and a drawing related to your project, your SolidWorks final project. We're going to collect homework 10, which was cutting the plate. So it'll be collected and it'll be bolted down to the table, right? So 10 and 12 are kind of, I'm going to grade them at the same time. I'm going to collect homework 11, which is rough cutting your little cube. And you need to have your name on there somewhere engraved. Okay?
We haven't shown them the engraver yet.
I'll bring it out. I'll bring it out this afternoon. It's basically electric pencil. So you just write like a pencil, but it's plugged in and it engraves. Okay? And then homework 12 needs to be bolted on there. And we're going to collect take-home quiz 3, which was the drill and tap quiz. So you got a lot due tomorrow. Most of it should be done already, but it's due. Any questions there? Yep.
Is the material for homework 10 and 11 going to be in the machine shop?
Yes. It's out on the table, the main workbench. I even labeled it. And we'll be around this afternoon to help you. Okay. Is that it for you? Okay. All right. Let's, for our remaining time, let's try and finish up this lecture. Fastening. All right, so there's another type of threads. I don't need you anymore for my bell. There's another type of threads called all thread, which is basically a bolt or a screw with no head on it. And that's useful for real long lengths where you need to put something in tension or compression in a very long length that you're not going to find in a bolt. So it's called all thread. They come in really long lengths if you want to. It's good for hanging stuff. Okay, glue. Let's move into glue. Super glue is also cyanacrylate, or it's commonly referred to as CA. So if you hear somebody say CA, they mean super glue. Okay? Super glue is really strong, but one of the problems is it can't fill gaps very well. So your surfaces have to be very close together, and they can't be rough. They have to be pretty smooth surfaces. Acetone dissolves it. So if you want to dissolve cyanacrylate glue, if you stick your fingers together with that stuff, it sticks your fingers together. I'm sure you've done that before. You can dissolve that with acetone, And if you don't have pure acetone, find a girl, because nail polish remover has acetone in it. It's mostly acetone, so you can use that to dissolve the super glue you stuck your fingers together with. Epoxies are typically two parts. They have a base and a chemical hardener. You mix the two thoroughly, and then you apply it, and it cures. And they have all different kinds of cure times that go with that. So there's literally hundreds of formulations. You have to pick the right epoxy for the application that you have. There's tapes, like duct tape. That's a water-resistant tape. That's what it was designed to do, is hold while it's still, if it gets wet, because it's a cloth weave. So it doesn't really need the stickiness. It uses the cloth nature of the tape for its strength. You've got aluminum tapes or metal type tapes, and you've got double-sided tapes or foam tapes, all different kinds of tapes. Like I said, gluing, huge warning for you as engineers. Adhesion is tricky. You can't trust it. It's hard to model unless you've locked down most of these parameters. I was telling the other team, the other class, the Boeing 777, the Dreamliner, is a composite wrapped fuselage, and it uses a resin and it cures. Well, they can trust their modeling on that because they've locked down all these parameters. Their surface preparation is extremely homogeneous. Their temperature and humidity is controlled in their manufacturing facility very accurately and precisely. Their consistency of the thickness of the resin they apply is very, very consistent because of the machine that applies it. Their mixing methods are well empirically understood. The consistency of the application, their curing times are done. They have very skilled technicians doing these mixings and adding these chemicals, and therefore they've done all this and researched all this, and then they've strength tested these over and over and over again, and now they can trust those models. You won't be doing that. You'll be going to Home Depot and McGuckins, buying epoxy, buying glue, buying it online, using it in a lab somewhere around here where the temperature fluctuates plus or minus 10 degrees. The humidity, it's 100% today. It might be 7% tomorrow. Who knows? You're not experts. Your surface preparation may not be perfect. So you've got to be very, very careful with gluing. If you are going to glue, first of all, don't think that you can model the strength of that. So you use glue on components that you don't really need to have a very good model for the tensile strength. And do these things. Clean your surfaces very carefully. You might start with soap and water and then use a solvent like alcohol or acetone. Roughen your surface by abrading them with a sandpaper or something equivalent. That will give you more surface area, little bumps for that glue to bond to. Follow all the instructions on the glue. Don't take any shortcuts. Don't trust it. Apply the glue to both components if you're putting two things together. Do it to both and then squish it together. Okay? Work it together. Kind of move it together and then push it into place. Don't just stick it on. Okay? Any questions about glue? Aerospace engineers don't use glue very much, so be careful. Some other adhesion methods. Soldering. Soldering is a process by which two typically similar materials are put together by a third dissimilar material. And that third dissimilar material typically has a little bit of, it's an alloy of the material that you're trying to add. All right? Soldering is typically a low temperature process. The important thing to understand about soldering, especially for Captain Electrical over here, is that the torch or the heat source is not what you want to use in order to melt the solder. You want to use the base material. In this case, this is a copper wire with probably a lead tin solder mix and a soldering iron. Notice the soldering iron is underneath the copper and the solder's on top. You want the copper to melt the solder. You don't want the iron to melt the solder because if the iron melts the solder, it may just melt on the surface and not properly adhere or bond to the copper. The same thing goes for this copper pipe. You don't want the torch to melt the solder. You want to heat the copper and have the copper melt the solder. It's very important. Questions there? If you don't do it right, that's typically called a cold solder joint, where it wasn't hot enough. It didn't melt the solder into the material. Brazing. You might hear about brazing. Brazing is fundamentally the same as soldering. It's just at a much higher temperature. Typically, solder melts at, I don't know, 150 or 200 Fahrenheit, something like that. Brazing's way higher. It's way up in the 800, 900, 1,000 Fahrenheit. Okay? Because of that, it can form a much stronger bond. But also because of that, it's very important that you pick, and the same is true for solder, but even more so in brazing, that you pick the correct alloy to put the two materials together. This is a well-known science. So if you're going to, for example, you're going to put two pieces of stainless together, they typically use some sort of brass alloy. If you don't know, you should go look it up or go ask people, supply companies for brazing. Make sure for brazing you pick the right brazing alloy for the right material. They also use something called flux, and you do that sometimes with solder, but not all the time. Flux is a chemical component that will, when the heat is applied, it will remove any oxidization or dirt or contaminants from the area. In soldering wires, typically the flux is inside. It's called flux core solder, where the flux is inside the solder itself. On a copper solder or on a braze, you tend to paint the flux on before you heat it up. Brazing. Questions there? And then there's welding, and that is dissimilar from soldering and brazing in that you're not joining two different materials together with a third material. You're literally melting the two materials together. Okay? So they have to be similar materials. You can't weld steel to aluminum. I'm telling you, people have asked me that over and over again, and I've even had students argue with me that you can do it. No, you can't. Steel doesn't weld to aluminum. You're melting a material and a material together. They have to be close to the same, similar molecular structure so that when they cool, the molecules bond back together. Otherwise, you don't have a molecular bond. Okay? Steel has a way different molecular structure than aluminum does. They're not going to bond. Okay? Some points that you need to know as engineers, and this is critical. The weld will never be as strong as the original material. It won't. Okay? Know that. High heat. You're applying a high heat. Steel melts at 2700 F. Aluminum melts at like 1400 F or 1700 F, something like that. You're applying a lot of heat at that joint. All these little molecular bonds in this material, they're all grabbing each other. So you got all these little valence electrons, they're all holding on to each other, right? Well, when you apply heat over here, that breaks that bond temporarily, but these bonds are still holding. So if we were all holding hands, and one of us, let's go over here, and then we reattach to someone else's hand, all these other ones are still holding and pulling. So it's going to, applying that heat is going to relieve internal stresses in the material, and it's going to warp your material when it cools. Because all those guys that are still holding hands are going to pull on that melted material as it cools. It will warp. It will deform your parts. So if you have high precision joints that have to go together, and you think you're going to weld them, and you think they're going to go together right, they're not. So be aware of that. Welding's not a super accurate thing. It's for putting two things together, and it's not a very super accurate or precise process. Yes?
For welding, do you layer the material or do you weld it adjoining?
So there's a couple of different types of welding. You can use heat combustion to weld. Usually you use an oxyacetylene torch, like I showed you. That introduces a lot of impurities because you're burning a hydrocarbon in order to melt it together. Then there's arc welding, and there's a lot of different types of arc welding. In this case, this guy is MIG welding. There's TIG welding, it stands for tungsten inert gas. There's stick welding. All those are forms of arc welding in which electricity electrons are passed at a very low voltage and a very high current through across the gap between an electrode and the material. And the flow of the electrons, the current, is so high that the material can't handle it and it melts and puddles together. Then you release the flow of electrons and it cools together and it rebonds molecularly. Does that answer your question?
I meant for how you weld it together. Are the materials layered on top of each other?
Oh, there's all different kinds. There's all different kinds. So this is called a butt weld. This is called a lap weld. There's right angle welds. There's all different kinds of welds. Those are geometries of welds. I'm just trying to tell you the method. Tolerances will not be predictable. You will introduce impurities into the weld. It's inevitable. You're applying a heat, which is a catalyst, and stuff in the air is going to get in there. It just is. Internal material stresses will be introduced. Like I said, that's all those little molecules pulling. When you relieve that stress in one area, but have it still in another, as it cools, you're going to have different stresses, and that's why it warps. It's not typical for space applications because in space you'll have vacuum, and when you weld, you're going to introduce little air pockets into the material, and typically that's not good for vacuum applications. So you're not going to see a lot of welding in aerospace. You will in mechanical. They weld all the time. It's a quick, easy way to put things together. Welding's a skill. You can learn it in about 5 minutes. It's like poker. You can learn how to do it in about 5 minutes, but it takes you your whole life to master it. So be careful with welding. Other questions with welding? That's the end of the first fastening lecture. It's probably a good place to stop, although we have a few minutes. Any other questions? I think I might start the second one. Oh, no, I won't. A couple of things I was reminded of that are typical engineering student blunders with threads. So I told the first group, but I forgot to tell the second group, if you ever see a person put Teflon tape on straight threads, you know they're a moron right away. Okay? Teflon tape only belongs on pipe threads. Straight threads are for tensioning or compression, pulling axially. Okay? They don't seal. They're not for sealing. All right? Pipe threads are for sealing, and therefore you use Teflon tape on pipe threads. So don't ever put Teflon tape on straight threads. Let me give you a few other no-nos. If I take a piece of aluminum and I thread the hole through with a right-handed tap, okay, so a standard tap, can I insert the screw here? Yes. Can I insert that screw there? Yes.
Left-hand side?
Yes, you can. If I tap all the way through with a right-hand screw, I can screw this screw in this way, and I can screw this screw in this way. And it's the same direction each time. It's clockwise each time. Okay? So, that's a common blunder. People think you can't do that. The other common blunder, because people thought the opposite of what I just said here, engineering students will often tap one way and tap the other instead of tapping all the way through. They'll run the tap in that far and they'll run the tap in that far. Will I be able to take the screw and run that all the way in?
No.
No. Because right here in the middle, you cannot guarantee that those two thread peaks will line up. They will probably look like that, and that will prevent the screw from turning. Okay? Third, blunder that happens all the time. If I have a piece of 1/4-inch material and I want to bolt it to another piece of 1/4-inch material, do I thread both pieces? No, you can't. No, you can't. This will not work. Your screw will go through this one and jam on the first thread right here. And the reason is, if you look from this direction, let's say this is my plate and I threaded my hole. When I start the thread, it starts at an unknown location on this circle. Okay? On the next plate, you don't know if it's that same location. It could start there. So as this screw comes through, you can't be guaranteed that it's going to pick up that lead thread right there. You never, never, never do this. What do you do instead if I want to put those two plates together?
You have to lock them together and tap it at the same time.
You could do that. That is possible. And I've seen it done before. And it will work the first time. The problem is, you're going to throw a burr right here. You throw burrs no matter what when you tap. Typically, we deburr those. Well, when you deburr them, then the threads won't line up again. So you could do that, but it's not typical. What should you really do? Yeah.
Tap one, and then drill through the other one just normally, and then do
Right.
that.
One should be threaded. The other one should be a clearance hole, either free fit or close fit. This would be close fit because it's close to the diameter of the screw. Free fit would be out here because it's a little bit bigger. It allows you to move the screw back and forth a little bit more slot. Okay? What kind of fit would we have wanted on our little electronics box to go on there, since we're not very good at measuring? We want a free fit on those holes. Okay? So, if I put a bolt in here, it goes through here without touching it. That's called a clearance hole. And it threads into here and pulls this plate into that plate. Okay? Those are the most typical blunders people make with threads. Any questions there? Any questions on homeworks? See you tomorrow.